dog. Okay. 2 weeks ago, this one here is available 2 weeks ago in the repository, so you can pull this one up and look at it. It's got a little more notes in it. I picked my shorter trimmed one here just for brevity's sake because I'm really just kind of the intro. And just want to cover back up here that what we had is we had a input array. We had an output array that we could test it against. We had a little nonlinear derivative, a little sigmoid bit of math right here. And then down here.
Also, for the grid, let's make them all the same letter for the box. I forgot to make that point clear, but hopefully you're not halfway through the grid. But they, all got to be the same letter.
Yeah, we said that.
Okay.
But that's good. Same letter. The whole page. Okay. This is the bit of the math that did the actual work of calculating the weights through each cycle. And then this was the output. You'll notice there's zero, very low here. This was the input, 0011. It does this 10,000 times, and we get very close to 1. If you do a rounding, you can get zeros and ones. Okay? Now, I've taken this and put a Keras layer in it. And this one is not up on the repository yet. I'll give it to Zach and he will get it up there after I'm done. So I'm just going to point it out and then you can see the difference. We import Keras. This is okay. It's a big red scary message that says everything's fine. Don't let it bother you. Okay? Come down here. This is the actual model where you classify it as sequential. Then you make a few options here. If you go to the read the docs, you can get things like this. Here's the sigmoid, which is the same thing as we did mathematically on the previous one. It just maps it to an S shape, keeps everything between 1 and -1. We have down here where we actually compile them on, and it's just one layer, real simple. It's an input of 3, output of 1, uses a sigmoid activation, so it's actually mathematically similar to the previous one. The model compile, I use the atom optimizer. There's about 8 of them listed, and all the optimizer is a way that it picks how big of a change to make. Straight up TensorFlow, you can set the number at like every 0.001 or something like that, which it could take a long time to finally arrive at home. This one, it takes bigger bytes and kind of slows down and takes smaller bytes when it gets closer. There's you can just pick them, but Atom's a nice safe one to start with because it'll get you close enough and then you can fine tune it past that. Same goes with binary cross entropy. I just picked that one because it was ones and zeros. I have no idea if I got that right. I didn't read up on these guys here. And then the metric accuracy because that's what it's going to display. Same input. I'm not going to run it. I just want to point out here that I tested this one here using Keras 010 and I got 0.4435. And this wasn't in the set. This one's outside the set. I just want to see. It should come back as a 0, so it should be less than 0.5. It's close, but it's still correct. So my accuracy is still 100%. If I scroll, I get the 1. Okay? And down here, just to brag, there's a 010 with 0.448. So it's an equivalent neural network. One's done with Keras, the other one's done with math. If you hate maths, as you say in the other country, use Keras. Then you don't have to know maths. Okay, I'm going to give that to Zach so that it'll be available for you to upload. And then the homework would be just to see if you can take the other one and add Keras to it yourself and just replace the little math bit because it's just the one line. Where that one little block that did the whole looping is just the one line in Keras. So it's pretty cool. The one I'm going to give you is going to have multiple lines. See if this is it. Yeah. I had added, and you can run these out where I added more layers just to make it slower, more complicated, and less accurate. Don't know why, but that's part of the fun about this is you can just go ahead and try the different activations. Any questions? I'm out of your way. What's that? What's that?
Where are you going?
I was just going to go sit down somewhere else.
Okay. I'll follow you.
Because he's got his. Oh, you need my computer?
Yeah, but do we get stuff? Oh. I thought he was for this yet.
Yeah, go ahead.
With this? Okay.
Doesn't like me. Hey, there we go. All right. Okay, is this readable for people? Or do I need to zoom in more? Good, okay. So there is a rather famous sort of beginner data set called the IRIS project, or IRIS data set that I can't remember the guy's name, but somebody, Fisher maybe, came up with in the 40s for 3 different kinds of irises. You can see them in the pictures here. And this first one is labeled because I imagine that the first question most people ask is, what is a sepal? Because that's going to come into account here. But basically the petals here and the sepals here are the points of data that we have for these flowers. And this data set has 150 total entries, 50 of each category. So there are 50 iris versicolor, 50 iris setosa, etc. So the point of this is to make a neural network with Keras that can identify which one it is given the data input. And so the input points of data, let's see, I skip down for a second here. So input data looks like this. It's got the sepal width and length, the petal width and length, and then the last field, I've actually slightly modified this data set. The only difference is that in the original, the 0 on the far right side there for class was a word. So in the original data set, it says iris setosa. I changed it to 0 just so I wouldn't have to do that in the code later. So setosa is 0. Actually, I think I listed this out. Yeah, 0 means it's a setosa, 1 means it's a versicolor, 2 means it's a virginica. And just so you can see it without my fancy table formatting here, each line of the file looks like this. It just has the numbers. They're all width and length in centimeters. And then the last one is the class of the iris. Later on, if you're looking at this and you want to get to the original data set, there's a link to it right there. And so I go ahead and load it in just using NumPy. So you might notice up here, imported our standard import NumPy as NP. I've also used Matplotlib to do some of the plotting stuff. And we'll come back down here. So NumPy has this handy function built in called loadtxt, so I didn't have to write my own function to import that comma separated value data. I just tell it the name of the file I want it from, and then the delimiter is commas, nice and easy. And just to show that it did the right thing, I'm going to print out the shape here, which any NumPy array or data structure is going to have this shape method that you can call, or property that you can call, and it will say what the size of that data is. So in this case, I mentioned it's 150 flowers, so there are 150 lines, and each line has 5 data points, well, 4 input data points and then 1 classification. So 150 by 5 is what you'd expect. And just to even further demonstrate that, I printed out the first 3 after importing it. So this is what it looks like internally now. You've got your 4 numbers and then your classification on the end. So one of the things that I thought was interesting about this data set is that if you go to the link to the original data set, the person who put together that synopsis says that one of the interesting points about this data is that the first set of irises are linearly separable from the second and third set, but the second and third set are not linearly separable from each other. I had no idea what that meant at first, so I thought, all right, I need to figure out what this means and what it looks like too. So as far as the neural network stuff goes, you can ignore this entire code block. The whole point of this is to draw that linear separability. And what it looks like is this. So this set of reds is the iris setosa, and the sets of blues and greens are the virginica and versicolor. So when they say it's linearly separable, it means you can draw a line between, all the red dots here and the other ones without having any overlap between the two. And that's much, much easier to see on this side. With the sepal length and width, you can do it, but it's not quite as obvious because these two data points down here are pretty close. But over here on the other one, it's pretty obvious. You could draw a line between those, no problem. So I just thought that was interesting. It's not relevant to the neural network, except that you might look at this and go, oh, well, if these data sets are all clustered really close together like that, from a standpoint of drawing a line on the graph, that's kind of hard for you to do without intersecting the two. Maybe that extends to the neural network. Maybe it's tougher for the neural network to figure out those 2 and 3 classes versus the 1 class. So just an interesting data point there, I thought. So anyway, I'm going to take the training data and I'm going to slice 45 of them. So hopefully everybody remembers the Python and NumPy slicing. And what I mean by this is of the 50 setosas, I'm going to cut off the first 45 and use those to train the network. And I'm going to use the last 5, so I'm doing a 90%, 10% thing here. Use the last 5 of each set as my test data. So after the network's trained, I run my last 5 through and see what it comes up with, see if it can properly identify those. Because we already know what the answer is. So the question is, can the computer figure out what the answer is? So basically here I've taken the first 45 of the data set, and then I'm appending. So the thing about this input data set is that they're just in order. The first 50 are the setosas, the next 50 are the versicolors, and the third 50 are the virginica. So basically I had to slice it here just to take 45, 45, 45 out of each set, and then I sliced it again doing the same thing, but only the rest of the 5 that I didn't take the first time. So hopefully that makes sense. I'm not sure I can really describe that really well. I can draw a picture actually that makes it really easy. So here's my set of all data, and I'm not really great at proportions, so just assume that these are equal. So this is going to be the zeros or setosas, this is the ones or versicolors, and this is the 2s. And so I'm just taking the bottom 10th of each of these, and that's my testing data. So training, 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 testing, testing, testing. If anybody has any questions, feel free to stop me. I'm not uptight about that. So anyway, I also just printed out the shape. So remember earlier I said the shape of the data is something you can always look at. Since I have sliced 5 out of each set, that's 15 total. So now my data set is 135 long instead of 150. And my test data is 15 long. And just to further show that, like I did above, I'll print out the test data. So this is all the data that we're going to use to test the neural network after it's compiled. And then following the typical uppercase X, lowercase y trend, I have separated the data out. So I mentioned earlier each line has 5 values. We only care about the first 4 in terms of the input data, and the 5th one is the output. So what I've done here is just say, okay, the X training data is the first 4 values, and then the Y training data is the last value. Again, NumPy slicing here. And then I did the same thing with the test. So the X testing data is the first 4, and the Y testing data is the last one. But notice up here I use trained data, and here I use test data. So it's the different data sets that were sliced up above. So then, because our neural network is going to spit out a series of values that are between 0 and 1, you might think, okay, how does that mesh up with the output data set? Because the outputs can be 0, 1, or 2, right? So previously, I don't know if everybody was here for those discussions or not, but there was one point at least where we went over one-hot encoding. And if anybody is not familiar with that, it is this right here. So because our outputs are going to be between 0 and 1, the 2 doesn't necessarily mean anything to it. So we one-hot encode it. So in this case, what that means is this first answer here, because this is the output data. So this first answer is a 0, which means we put a 1 in the first column. So these columns correspond to 0, 1, and 2. The first 5 in the test set we know are zeros, so they have a 1 in the 0 column and a 0 in the other columns. The second 5 are 1s, so they have a 1 in the 1 column. The last 5 are 2s, so they have a 1 in the 2 column. Anybody have any questions about that?
Could you just run through
Okay, well, so let me draw it out. This might make more sense. So for the test data, I have 5 of each one of the test data set. So that's going to look like, there are going to be 5 zeros, there are going to be 5 ones, and 5 twos. But since the neural network can only spit out 0 or 1, we have to have a way to make a binary answer basically correspond to a non-binary data set. So if we were to draw out the whole data set, something like this, these would be zeros, ones, and twos, but we need to also separate them in a way that is able to be understood and represented in binary, 0 or 1. So basically what I say here is, so this is going to be my flower class, 0, 1, and 2. And then over here is going to be my one-hot encoding categorical change thing. So hopefully this will make sense. So like since the first set are all 0 class, they're just going to have a 1 here, which means check mark turned on. These are ones, everything else is a 0. Does that make sense? Okay. And you may notice here that I used this nputils toCategorical because NumPy has a neat little function called toCategorical that does that for you. So, again, you don't have to come up with your own algorithm to do one-hot encoding. It's got it built in. Okay, and the fact that this is categorical data will come in, will be important on the model compilation and fitting as well. So now we get to the point where we define the model, and I will admit up front that I am not an expert with any of this. I played with this until I got the results I wanted, but I don't know all the answers about why you pick what you pick. We will be going more into this in future workshops, so don't feel like you need to understand, what each layer does exactly right now, because we'll get into that more. But a couple of things that I wanted to demonstrate are like this first layer. So first off, we create the model as a sequential model, and then the very first layer. A lot of times you will see, since this data set has 4 inputs, and a lot of times you'll see the first node of the neural network have 4 neurons because it's the same. I should reword that. You'll see usually the first layer of the neural network have the same number of neurons as the number of input data features or data points. But what I was trying to describe here or show here is that it's not required. I could, if I wanted to, comment this line out and then uncomment this other line, and these do more or less the same thing. They don't come up with exactly the same numbers, but I can create this first layer with 10 neurons if I wanted. I just have to tell it that my inputs are only going to be 4 instead of 10. So just kind of an interesting data point there. You can do it either way, because there are 18 ways to do any given thing, right? So then, technically by convention, this is not a deep learning network. Anybody know why that is, just off the top of your head? It is a machine learning, but not a deep learning neural network. The reason for that is because as I have it here, there's only one hidden layer. We've got our first layer, we've got our end output layer, and then we've got this one hidden layer. If it had more than one hidden layer, by convention, it is a deep learning network. Just a little bit of, yeah, just a trivia. That's not necessarily useful, but I found that interesting. So anyway, I have, just by playing with it, come up with a hidden layer with 32 neurons, and I'm using the ReLU function, the rectified linear unit that I think Zach went over previously. As another interesting graph kind of data point, what the ReLU function actually looks like is kind of interesting. So I think previously he talked about sigmoid, right?
Yeah.
And the sigmoid looks something like that, basically. Pardon my terrible drawing skills. ReLU looks like this. And what it means is it basically gives you the maximum of either 0 or A, where A is, in this case, to dumb down the example so that I can understand it, this is just an x coordinate. So A is the x-axis. So if this is 1, then the ReLU function returns 1. If this is 2, the ReLU function returns 2. If it's less than 0, you get 0. So another way of normalizing, flattening, well, flattening is probably the wrong term, but normalizing your data here. So another thing that's interesting, I'll show off a little bit, is I can add this second layer here, which has a different number of neurons that I picked completely arbitrarily, but I'll be able to show that it gives different numbers there. But anyway, I'll come back to that. The last layer is, and you'll notice these are all dense layers. The last layer is 3 because my output is going to be one of 3 things, a 0, a 1, or a 2, depending on the class of the flower. And then softmax is the activation I chose for this because that will, softmax will keep the output values between 0 and 1, and I'll demonstrate later that all 3 of the values that it spits out in terms of its, how sure it is that the flower is one type or the other, they will add up to 1. So it'll be X% sure that it's a 0, Y% sure that it's a 1, Z% sure that it's a 2. All of those are going to add up to 100% or 1. So then we go ahead and compile it. The loss function I picked here is categorical cross entropy. You saw Dennis used the binary cross entropy earlier. Anybody guess why we used the 2 different ones here? Okay.
Demonstration purposes.
No, not just demonstration purposes, but in Dennis's example, the answer was binary. In my example, it's one of 3. It is actually categorical versus binary. So the loss function you pick, while there are other factors that I'm not even aware of, I'm sure that go into it, just at a basic level, binary cross entropy would make more sense probably for just a 0 or 1 output, whereas categorical makes more sense for a 0, 1, or 2 output. Or, up to 10 or 50 or 100. Optimizer, I'm honestly not sure what the best one would be for this. I just picked Atom because they say it's a good one to use. So if you are interested in reading about that, I can add some links to Slack about it. But somewhere I have here, the gentle introduction to Atom. And this guy, the machine learning mastery guy who has so many good articles, has an interesting introduction to that. So I will share that later if anybody wants to check it out. So anyway, we compile that. The metric we care about is accuracy. To be honest, nothing that I've done so far I've cared about anything but the accuracy, but there might be other metrics, and depending on what you're doing, that you want to track. So then we go ahead and we fit using the training data. So we use the built-in fit function here. We pass it our training X, our training Y, and this is the one-hot encoded training Y data. If you pass in the normal training Y, it just throws an error. It says, I expected 3 numbers here, I only got 1. So when we one-hot encoded it, each one is going to have 3 numbers based on whether, that chart over there, whether it's a 0, 1, or 2. Then, so as far as knobs you can tweak, you can change the number of epochs. I started with 100 because it's good enough for this data set, but I'll show later if I change it to 300, for example, it just gets a little bit better. The batch size is an interesting one. I had to ask Zach about this and look it up. I was thinking originally that batch size only affected how fast your computer ran the neural network fitting, but it turns out that's part of it. But the more important part of it is that with a larger batch size, you're giving it more data to. Help me out with the terminology here, Zach. You're giving more data for the gradient descent, or was it for backpropagation, or both?
Both, yeah, both. So you specify the batch size when you have computational constraints on your computer. If you say that you're trying to work with a very large data set, you can't train it all at once. Then you want to break it up into parts and work with that enough times, and then you take in this case 10 observations at a time, train it on that, and update the network on those 10 at a time. There is a bit of a trade-off that the smaller the batch size, the more variable its weights will be trained. It'll be more sensitive with each incoming data set.
Noisy is also a word I would use there.
Yeah.
Overtraining happens easily.
Yeah.
I mean, ideally, you'd want the batch size to be as big as possible that you could stand it to run.
Yeah. There's a trade-off for computation time and complexity.
Right. So when we get to like the image recognition on our own computers, we would be dealing with small batch sizes. Each computer would have a different batch size that's appropriate to make it work within each epoch or not overload, not use up too much memory at a given time.
Right. So as a side note, I mentioned that because it's one of the things you can tweak, or as I say, knobs you can tweak. The default batch size is actually 32. I turned it down, not knowing that at the time. I just picked this number pretty arbitrarily. But if you left it out, it would be doing 32. So anyway, that runs through the fit. Good. Takes a few seconds to do it here. and then we evaluate that. So now that we've trained the neural network and done the fitting, we use the test data that I separated out earlier, the 15 sliced data that we know the answers for, and we just check using the built-in evaluate function how the neural network does against those. Because we know the answers, we just feed them in, and so the computer can go, oh, okay, I was 100% right in this case, or not. For this data set, it's 100% right, although there is some loss. And that's another thing that I'll show in just a minute. We'll change a little bit. So if we want to see what those predictions look like, I've printed them out in two different ways here. The first is just, this is what the raw numbers look like. So you'll see, and like I said earlier, the softmax function means that this number, and this one all add up to 1. So there's obviously some rounding going on here, but basically what this says is it's 99.7% sure that this one is a class 0. So remember, if you remember the one hot encoding, these first 5 are going to be pretty high numbers in the first column, and then very low numbers in the second and third column. The middle 5 are going to be high numbers in the middle column, very low numbers in the outside columns. And so I did the same thing, just rounding it off here. So you can see, oh, in the first 5, it was 100% sure. And this I bring up because I mentioned earlier the linear separability part, where a human looking at that graph could go, oh yeah, it's really easy to draw a line between the red and the blue and the green because the red are all way over here and the blue and green are clumped up over here. It's not easy to draw a line between the blue and green. And that's kind of borne out by the data here because you can see it was very, very sure, 100% sure about all the zeros. And then it was close to 100% sure about the ones. And then it was not very sure about this particular one, but it's still technically correct because it's 57% sure that was a 2, which it is. So, this still gives you 100% accuracy, but it was only 57% sure. It's like, I think that one's a 2, but could be wrong. So, and then I just did the same thing here, but rounding it all the way off without percentages, just to show that it came up with 1s for the first 5, or excuse me, 0s for the first 5, 1s for the second 5, 2s for the third 5. So I'll go back up here for a second to the loss. If I go up here and change just one thing, like for example, the number of epochs, I'll make this 300 instead of 100, and just go ahead and rerun. The things I love about having a mouse wheel that doesn't lock is I can just keep scrolling this until it's done. Okay, so you'll notice here, it's still 100% accurate, but look at the loss. It's much, much, much lower than before. And then if we go down here and look at the numbers as far as how sure it is, notice that one that was a 57 before, now it's 97% sure. And you can get similar results. I won't demonstrate this just because it'll take a while, but if I were to go up here and uncomment this second hidden layer, even though it's doing the same activation function, that's still going to increase. Well, it's not going to change the accuracy in this case because it's already 100% accurate. It's going to decrease the loss. So, hopefully that is understandable. Does anybody have any questions? So at this point in theory, if we had another 150 data points of these particular flowers, we could feed it in and see what it says. I don't have any more, but...
Did you show where you got the data set?
Well, I linked it up above, but I think actually that I have it open somewhere here. Yeah, here's the UCI. So the UCI machine learning repository has a bunch of different data sets, and that's where I got this iris one. So let's see. Yeah, down here it says the attributes that are available: sepal length, sepal width, petal and then the class. So it's just like what I suggested earlier. And when I was talking about this person mentioning the linear separability, this is the comment right here. One class is linearly separable from the other two. The latter are not. And that's what that scatter plot was hoping to show.
You did.
I thought it was pretty cool.
Yeah.
Yeah. Also, if you decide you want to go and look at them, Keras has good documentation for example, the sequential model API is one, and the core layers. This example, I used all dense layers, but their documentation is pretty good about, not necessarily about figuring out where you would want to use a particular type of layer or the other, but it's good about telling you what inputs go into that layer when you create it.
So, or would have been, you know, if it were happening today.
So we can bring this on our next cruise.
Yes. If you buy a ticket, you're likely to.
Could be something interesting to play with.
No, it doesn't, but it's purely by, so female first class, of course, we're more likely to survive, and then male third class, you'll find out once you run the program back this week. No, you can pull it, you can just.
Good
pull it in a
flotation.
second. Yeah. And try it.
No worries. So, anything I need to clarify or add to, or
And yeah, we're just gonna use the remaining time.
But
You
I
guys
also
can use to play with the notebook, turn the knobs, try playing with the different things that he pointed out. And if you have any questions on how to do that, we can help guide you.
as another useless side data point, this is running in Amazon EC2. You can't tell that by looking at it, but I'm running this in Amazon with a non-GPU instance for what that's worth, but it'd be trivial to set up one with
Is that still on
GPUs.
the free?
This is the free tier. So even when I ran that with, actually, let's do this as an experiment. I will leave it set to 300 epochs, and I will time it, and we'll just see how fast the crappy free tier of EC2 can do. So I'm going to import poor typing, and then down here when we actually do the fitting,
Import time?
so we do T1 time, and then down here.
It's A for above, it's B for below.
Okay. Okay. So let's see how long it takes this free tier T2 micro Amazon EC2 instance to do that.
Shows you a point.
It took 8.78 seconds. So the cheapest, crappiest tier of Amazon instance took 9 seconds to run 300 epochs of this neural network. So, I thought about showing off
Somewhere first line.
what's that?
So
Which first line.
Your T, probably T1.
Oh, it's the same as T2, just time.time.
So go back up a couple cells from where you are now. I'm wondering if
Oh, actually, this was the wrong one. I didn't mean to run the one with both layers. So let me rerun that real quick. So it probably will take fewer than 9 seconds. Yeah, it was not really much different in this case. 8.5 seconds. So anyway, what were you saying, Zach?
yeah, where you compile the model, we just had it such that you must specify the input dimensions for the first layer on one of our computers here. So I'm wondering if that is different for different environments. But it would
Well,
work if you did not specify the input dimensions.
we ought to be able to figure that out if we go and look at the documentation for the dense layer and see what it says about. Okay, well, it doesn't really say anything.
Right. It just gave an error saying that the first layer must specify the input dimensions.
Yeah, that's strange because, I mean, as you can see, this one doesn't.
Yeah, and I've seen you.
Maybe it's just
There
a,
may be other variables into this force that.
or it could be a different version of Keras.
Possibly.
But yeah, so I mean, I could do the same thing by just adding input dim equals 4 here. But in this case, I didn't have to because it is a 4 neuron layer. But yeah, so this is the cheapest tier of Amazon EC2, which for the first year is completely free. So I'm not paying anything right now to run this, and even that only takes 9 seconds. So What I was going to say earlier is I thought about trying to do this on a GPU instance just to show off how fast GPU computing is, but this data set and neural network are too small to make that an effective, demonstration at all, because it won't really be. It would be faster, I'm sure, but it wouldn't be enough faster to drive the point home. So later on, when we get into doing the MNIST data set, which has 60,000 plus inputs, and we'll have a first layer of 784 neurons or whatever that comes out to, it'll be really interesting to see how much faster a GPU is there. And what I actually really want to see is a combination or a comparison of three different things. I want to see, for example, how long it takes to run on the CPU on my laptop, for example.
3 seconds or more.
Okay, so there's a good example. Or the CPU on this Amazon instance versus a GPU in my home computer, which is a gaming GPU. It's not optimized for neural networks or data science or anything. It's just a video game video card. However, it should be a lot faster than the CPU. And then the Amazon GPU instances, which use the actual Tesla, neural networks math optimized cards. So I think it'll be interesting to see those three, because the first one's going to take a long time. It might take 3 or 4 hours to do an MNIST thing. Might take more, might take less. But I expect that the GPUs are going to be an order of magnitude faster than that, or multiple orders of magnitude faster. So yeah. All right. Any last questions or anything before I pack it in? All right.
No, is that out on the repository?
It is. The version with the time calculation, since I just wrote that, isn't there, but everything else should be.
So it should be
Play with this properly, we have to have the data set like the other one.
In the GitHub repository, the data set is included with it. There should be 2 files in that folder. Actually, let me go back and show where that is.